Welcome to our webinar, Rethinking the Paper Cup, Designing for Recyclability and Compostability, brought to you by SAM North America and NatureWorks at the TAPPI, International Flexible Packaging and Extrusion Division. I'm Andrea Auchter, NatureWorks Application Development Engineer. I have 16 years of industry experience between NatureWorks and General Mills, where I was a packaging engineer. I'm a certified packaging professional by the Institute of Packaging Professionals, and I'm a certified SolidWorks associate. And joining me is Andy.
Hi, I'm Andy Christie. I'm Managing Director of SAM North America, equipment supplier to the extrusion coating industry. I've been around for about 35 years in this business. Last 10 with SAM, previously about 10 years with Extrusion Process Solutions, a consultancy serving the extrusion processing, and 15 years with Black Clawson, where I was the extrusion business unit manager. Been very active in SPE Flexible Packaging Division and TAPPI IFPED, and look forward to presenting our information here.
Thanks, Sandy. Today we're going to go through the evolution of paper cups and circular economy considerations. We'll cover the extrusion coating process for package manufacturing, and then we'll get to our experimental design and procedure, the results, and the conclusions of our study. So why do we have disposable paper cups? Well, prior to 1910, we had what you see in the upper right picture, the common metal cup, and it's attached to public water fountains. In 1910, the campaign against the common cup was initiated. This was to stop the spread of tuberculosis with some very graphic images. And it was even more relevant in 1918 when the Spanish flu hit as a way of controlling the spread of the flu. And you can see from the history of the Dixie cup, they had lots of advertisements about it. The second picture is, on railroad trips, no other lips have touched the cup that Phoebe sips. So there started the paper cup. And then we realized, we need a moisture barrier on this cup. So they were coating them with wax and kept developing and iterating. In 1957, the development of the PE coated cup, the polyethylene coated cup, was launched, thus eliminating staining of the paper. And development continues. In 2006, there was the first commercial compostable coated cup with PLA, which we will talk more about. So we understand why we need disposable paper cups. But what happens when we're done? Where do they go? What are some good end-of-life scenarios for these cups? The first one that comes to mind is obviously recycle. There's good fiber in these paper cups, long fibers that are good for recycling. So what would happen is these materials would be placed in recycle bins and sorted at material recovery facilities, or MRFs. And those all get into bale specifications. So the Food Service Packaging Institute has been endeavoring to have the paper cups included in bale specifications to get that really good fiber. And the American Forest and Paper Association is working towards having a post-consumer stream collected and accepted, which would look something like the picture on the bottom right there. That is a vat of paper pulp. So the paper comes in, it's repulped with water and hydrated to get those great fibers out. So this is a great end-of-life option. But what if you can't recycle it because it's contaminated with food? Another great option is industrial composting. Okay, compost is made by decomposing organic materials into simpler organic compounds in a process called composting. This is contrasted to simple disintegration. Disintegration is just a process of losing cohesion where something has mass and it breaks into smaller and smaller pieces, but never becomes bioavailable. So that brings in the concept of biodegradation. This is the consumption of organic matter by microorganisms such as bacteria and fungi. So to successfully create valuable compost, you have to be able to decompose into organic compounds that can be recognized by these microorganisms as food and processed. All right. What you see in the pictures is industrial composting. This is a manufacturing process with time, temperature, and moisture controls. And that's a lot different than if I backyard compost at home. I don't really pay attention to how long or what the moisture or temperature is in my backyard. So, backyard has a lot of variation. Industrial composting is a controlled process to generate compost. You can see two examples here in the pictures. We have the windrow on top, which is an actively churned compost to keep oxygen in. And you have the aerated static pile on the bottom, where it's static, no turning, but air and moisture and temperature are controlled. All right, we've talked about two great end of life scenarios for disposable paper cups. Is there a material that fits these? And you can design for multiple end of life scenarios. And we need to, with the circular economy being so important to our future. So, PLA is polylactic acid. And what happens is plants sequester carbon dioxide and greenhouse gases, and they make sugars in the plant leaves. We can take those plant sugars and ferment them into lactic acid, and then we can polymerize that into polylactic acid. So, PLA is bio-based because the raw material is lactic acid and is fermented from sugars. And once PLA is fully disintegrated, many composting organisms recognize lactic acid as a food source. In fact, we all have lactic acid in our bodies. When we have a hard workout, we get sore muscles, and that soreness is from the lactic acid that our own body generates. So, PLA fits in many end of life scenarios. It can be reusable, it can be mechanical recycling, and it can be chemically recycled by bringing it back down to lactic acid. And in organics recycling or composting, the PLA breaks down with time and temperature to lactic acid, which is recognized by those microorganisms. So, the coated paper cup normally is coated with low density polyethylene, and that has a molecular architecture that gives it melt strength. You can see a diagram in the bottom right there. This is what all of our history equipment has been designed for, and it has, like I said, great melt strength. PLA, you can see the diagram of PLA in the upper right, is a lot different. And so we've done what we can to increase that melt strength and viscosity in this PLA grade that we studied. It balances those two, melt strength and viscosity, to help with the extrusion coating. And beyond just looking at resin, you also need to consider the equipment. So now Andrea will take us through the extrusion coating process. You are on mute, Andy.
So I just wanted to start by reviewing the extrusion coating basics, and I've put up here a slide of a typical tandem extrusion coating line for paper. So this would be similar to a paper cup line. And every extrusion line has some of the same basic components. So we've got some sort of unwind, so we can unwind rolled goods into the machine process. There's usually some surface preparation. In this case, we're showing here a chemical priming. This could also be a corona treated. It could also be flame treated or treated with ozone to promote the adhesion of the polymer that's going to be coated onto the paper for good bond to the paper. For low density polyethylene, commonly run, it's coated on in a single layer. We can then turn that over. We can then pre-treat this again and then coat the opposite side. So this would be a typical configuration for an extrusion coating line, and that would include unwinding, pre-treating, the coating station where the polymer is applied, and then rewinding this product back up.
Is it not advancing?
I'm not advancing here, so.
All right, let's try this again. There you go.
Okay, sorry about that. Still not advancing.
There we
There we
go.
go. So this next slide, I go into a little detail of the extrusion part of this extrusion coating line. And the extruder for extrusion coating is assembled on a cart so that it can be brought into the machine to coat. We have the extruder with the feed screw in the barrel of the extruder, pumps the polymer through, typically through some kind of pressure valve, and down into a T-slot die. This T-slot die is positioned over the moving web, and the polymer is spread out through the die where it comes out as a thin film, which is then drawn from the lips of the die at a very low speed into the coating nip at a high speed. For low-density polyethylene, this very broad molecular weight distribution polymer with chain branching, which has a lot of melt strength, and in order to draw out of the die well at high speeds, we want to have that brought to a very high temperature, which also promotes the oxidation, which creates the bond to the paper. So in order to do that, we use a screw, which this is a typical high shear extrusion coating screw. This has a short feed section, a transition, and then a long metering, mixing, an additional metering and mixing. This is all done so that we have the time and the shear energy to put into the polymer to raise this melt temperature and get a good condition for low density polyethylene to create the temperature for the oxidation to get the bond as we coat. This is kind of the opposite of what we want for the PLA polymer, which I'll talk about here in a second. But I just wanted to show a configuration of another line, which would be suitable for making a completely biodegradable product. So the difference here being that we're going to start with a printed paper, and we're going to create a barrier coating with a metallized PLA laminated to this paper. We're going to unwind that substrate. We can again pre-treat that substrate, and then we can coat it with PLA for a sealant layer, or we can use that PLA to laminate a biodegradable sealant film onto this, which will then wind up creating a simple lidding type film for full biodegradability, because all of the components can biodegrade into the food for these microorganisms. We've got a variety of configurations of machines available to create different product structures, from simple single coating with priming for mono extrusion, or laminating, adding a laminate unwind in here, or adding some co-extrusion in, or tandemizing it, and again, tandemizing and adding co-extrusion. So there's many configurations that we can create depending on the product structure that you want to make for your finished product. The challenge for PLA, because of the different polymer structure of PLA and the thermal sensitivity of the polymer, we are limited in the temperature that we want to process this at. Typically, that is going to be 55 to 75 degrees Celsius lower than the objective temperature for low density polyethylene. So when we put the PLA into this high shear screw for polyethylene, it's going to overheat before we get to a reasonable output. So we're going to be limited in the extruder output, not because we can't pump that PLA, but because that PLA will go over the target temperature that we want. Additionally, there's often a back pressure valve, which again puts more shear energy into this. So it's very difficult with this arrangement to keep the temperature down at a reasonable output. Other challenges we have with PLA is because of this linear polymer, it tends to neck in more than the low-density polyethylene, which causes us to get useful sheet to try and lower the dye into the nip, shortening that air gap, which now increases the rate of extension of the polymer in the air gap, further destabilizing the melt curtain. We also are fooled sometimes. We're going to talk a little bit about I'll say the average temperature versus the indicated temperature of the polymer. And sometimes we can be fooled, again, because of the equipment that we're running on and not recognize the over temperature that we're putting into the PLA on conventional extrusion coating equipment. The viscosity of the PLA at these lower temperatures may also reduce the distribution to the ends of the die, which will also affect the stability at the edges. In our experiment, we looked at the drawdown ratio, and this is the change in thickness of the polymer as it leaves the die lips to the final coating thickness. A more rapid change of this, or a greater change in thickness, again, affects the draw of this polymer, and with the linear polymer, it becomes, creates more neck in and the instability. When we lower it down into the nip, it also draws at a higher rate of extension, and this also tends to contribute to the instability in the melt curtain. So what we do in our experiment, we looked at a couple different screw designs. So we took a conventional high shear extrusion coating screw and two additional lower shear screws to see how this would impact the melt temperature and the output. Essentially, by putting lower shear energy in, we're able to get a higher output from the extruder at that low temperature, which gives us better flexibility in how we run the machine to get the speeds and quality of product. The other things that we looked at were the drawdown ratio, which we were able to reduce by reducing the die gap, and the rate of extension, which is impacted by the air gap, so the distance between the die lips and the coating nip. We did one brief look at edge encapsulation, and that's introducing a secondary polymer only on the edge of the melt curtain to then allow for higher line speeds by stabilizing that edge. So this was all done for the ability to try and increase the line speed while reducing coat weight to create a PLA-coated product at reasonable production speed. The other thing we looked at in our experiment was the adhesion to the paper, observed the gels and unmelts in the curtain, making sure we're getting good quality melt without holes or voids. And then we subjectively looked at the edge weave and the curtain stability to make sure we're making a good product during this trial. With that, I threw this slide in because I wanted to just talk about this melt temperature. So this is our HMI screen from our lab machine. And we're all used to looking at a single point melt temperature on our control screen. And this can be a little misleading, especially when we're looking at materials that don't run as our conventional materials. So when we looked, we took during our trial, and we put an adjustable thermocouple across the pipe So if you think of the flow coming down through a pipe, we were able to measure from the wall of the pipe to the center and across to the wall of the pipe again. And what we saw on the high shear screw with low density, we had a fairly uniform temperature. We've only got about 3 or 4 degrees variation, and very close to our target of 325 with that high shear screw. A little cooler in the center because we weren't running up to the maximum speed possible with that screw. But here, when we went to the low shear screw, what we saw is a wider variation. We had difficulty with the low shear getting up to the high temperature we wanted for the low density polyethylene, but we also had a lower temperature in the center because of the low shear screw. When we put the PLA on these same screw designs, with a profile set up to get an objective lower temperature, what we find is the screw over shears and we get a high temperature in the center. And this is because of the difference in the polymer structure. The linear polymer and the viscosity tend to push this temperature up through the work. When we put in the low shear screw, we shifted that temperature down, but we still see an overheating in the center. So we also did a further adjustment of the screw design, and you can see here, when we add this further adjustment, we were able to further lower that temperature and reduce the overheating in the center of the screw. So the data that we're going to talk about further now is on the screw before this additional modification, and I'll let Andrea go over the further data here.
Thanks, Andy. Yeah, so the first part of our experimental design was finding what speed we can run the PLA where it's not degrading and get the most rate, but still have quality resin. Okay, so we increased the line speed and the extruder output in ratio. So we're maintaining a constant coat weight and we're increasing the speed. So the screw's going faster, the line's going faster. And the melt temperature is going to increase and increase with the extruder output. So you can see eventually we get to a point where above 252 up to 256 melt temperature in the center of the screen, that's really too hot for PLA and you're going to have degradation. And we observe outside coming down the melt curtain excessive fuming, very significant fuming. So we backed it back down to 112 kilograms per hour and a melt temperature of 252 and said we don't want to go any faster than that to maintain the integrity of the polymer. So we set our extruder output at 112 kilograms per hour. Moving on to the second graph, then we do a drawdown study where we maintain that extruder output and we increase the line speed, taking away that polymer, going faster and faster. And as we do that, it will thin the coating down. And so you can see the coat weight started off at about 22, and then it decreases as the line speed increases at constant extruder output. And we took that as far as we could until the onset of draw resonance, and then even past the onset till we were fully in draw resonance when we reached unstability. But the onset of draw resonance just before that was 7 micrometers thickness. So we're able to take that special PLA down to a thin coating with the correct line speed and correct screw design. Okay, in summary, we looked at 3 screw designs: the standard extrusion coating screw design for LDPE, a compromise or specialty screw design, and then a specialty low shear extrusion design. And you can see the comparison of output rates, and next to those are line speeds. So looking at just the standard extrusion coating, if you don't have alternate screws, this is what you've got. And what can be done? You can reduce the die lift gap and you can have an increase in your line speed of PLA by reducing that die lift gap to change the drawdown. So that's something you can do right away today. And that got 130% increase compared without the die gap reduction. Okay, if you have the compromise screw, that had lower shear and it increased the output of PLA because we can maintain that acceptable melt temperature at 253. We can get 107 kilograms per hour, which is an increase in 137% of throughput, and the line speed, 130% again. Now you can see the impact of combining these things. So if you have a low shear screw, you get increased output from your extruder, 119 kilograms per hour, and a lower melt temperature, 249. That's an increase of 153% in output. In line speed, that's 143% increase in line speed. If you do that and reduce the die-lip gap, you can get 186% of your line speed. And if you have edge encapsulation as well to help stabilize that curtain, you can get 200% line speed increase. So the recommendations are invest in that low shear, high output screw design for PLA, minimize your die-lip gap, keep your melt temperature under the critical 250 C or 482 degrees Fahrenheit. And if you have end encapsulation, include the edge encapsulation. So, capital investment is needed to gain output and reduce coat weights for PLA. The alignment of that screw design to new materials like PLA will increase that output rate, and it keeps that melt temperature. It doesn't add too much shear. It doesn't add too much melt temperature to the point where you're compromising your polymer integrity. This investment would facilitate market growth potential in coated cups beyond cups, so into trays. So we really see it as an investment to grow.
And I think the other critical factor here is that the structure and design of this polymer in itself improves the stability of this web, which allows us to get to these higher line speeds and the lower coat weights. And the stability and reducing edge weave reduces the amount of scrap that's produced as well. So this all goes to getting a coated paper product that is more viable in the market because we're coating with a little lighter coat weight and higher processing efficiency with the stable web and good adhesion. So we're excited to be doing this work with some equipment modifications that will allow us to improve the processing as we go forward with these new polymers.
Thank you for joining our webinar, Rethinking the Paper Cup. For further information, there is a white paper that has been accepted to the TAPPI journal, and that's currently available on the IFPED website. This has been brought to you by SAM North America and NatureWorks. And Andy and my contact information is here for further questions as well. Thank you.
Thank you all.